Welcome back. Today we're going to be talking about topic 1.4, entire and mixed radicals. To get started, let's take a look at our learning targets. In the first part of today's lesson, we're going to be looking at how to express a power with a rational exponent as a radical and how to express a radical as a power with a rational exponent. In the second part of the lesson, we're going to take a look at how to express an entire radical as a mixed radical in simplest form and how to express a mixed radical as an entire radical. We're also going to be looking at how to write an irrational number as an exact value. So before we get into converting from radical form to exponential form, it's important that we understand some of the terminology. So radical is an expression that consists of a root symbol, an index, and a radicand. This part here is the radical sign. And the little number inside the check mark is our index. And the number underneath the radical sign is called our radicand. So this first expression is a cube root. The second expression here is a square root. Notice our radical sign is that check mark symbol. And our radicand is the 64. So you may be wondering, well, where's the index? The index is 2. So similar to when I'm writing like 4, that means 4 to the 1. The 1 is sort of understood as being there. It's the same with a square root. If you just see the square root symbol, that's telling you that your index is 2. We have our individual pieces, the index, the radical sign, and the radicand, and that combined makes up our radical. Other examples of radicals might be the 4th root of 32 or the 5th root of 47. So depending on what our index is will tell us what type of root it is. All right, so let's take a look at example 1. It says for each radical, state the index and the radicand. So for the first example here, my radicand is 2/3. And my index is 4. Now, when we're talking about the radicand, that's the information that is underneath the radical sign. And so you might look and say, well, what about the cubed? This can also be written as the 4th root of 2/3 and then cubed. So because that 2/3 cubed is underneath the radical sign, it would be acceptable to write 2/3 cubed. Because this can be written in two different forms, you can also just write the 2/3. For the next example, my radicand is 32. And my index is 5. Again, if you wanted to write that as 32 squared, that would also be acceptable because this can be written as the 5th root of 32 squared, where it's just the 32 as my radicand, or the 32 squared. My last example, my radicand is 16, and my index is 2. Example 2 asks us to determine the length of the unknown side. So when we're looking at this triangle, I have a short side of root 6 and a long side of root 24, and I'm looking for the side opposite angle J, so that would be side J. This is a Pythagorean theorem question, so our standard formula is a squared plus b squared equals c squared. Because we're looking for a short side, we can do that by subtracting. So J can be the square root of root 24 squared minus root 6 squared. So that's just rearranging the formula to get that side length by itself. So let's say that's b squared. I'm taking c squared minus a squared, and then I'm square rooting to isolate the b value. In this case, our side length is j. Now to evaluate this, we have the square root of root 24 squared minus root 6 squared. Well, when I square a square root, I'm essentially canceling out that square root because these are opposite operations. So that leaves me with the square root of 24 minus 6. Simplifying under the radical sign, we would have the square root of 18. Now we're going to leave that example there, but we are going to come back to it because root 18 can actually be simplified further. Moving on, let's take a look at how we can convert between radical form and exponential form. So in this first example, I have a square and I'm telling you that the side lengths are 3 to the 1/2 and 3 to the 1/2. Well, if I want to calculate the area of that square, that's going to be side squared or length times width. So if I have 3 to the 1/2 times 3 to the 1/2, these are two powers with the same base. That means I can add my exponents. That would give me 3 to the 1/2 plus 1/2, which is 3 to the 1 or 3. So the area of this square would be 3. Now let's think back to a previous lesson where we were defining a square root. If I have the area of a square and I want to find the side lengths, I just need to square root. So the square root of 3 would be root 3, and the square root of 3 would be root 3. Since these are equivalent, that tells me that 3 to the 1/2 is equal to the square root of 3. And remember, my index is 2. Now, when we look at a volume example, you'll see that the same rules apply. If I have 3 side lengths and I'm trying to find the volume of this cube, that's going to be length times width times height. Because they're all the same, that's the same as saying side cubed. So I'm going to have 8 to the 1/3 times 8 to the 1/3 times 8 to the 1/3. Again, they all have the same base, so I can add my exponents. 1/3 plus 1/3 plus 1/3 is 1. So I'm going to have 8 to the 1, or 8. Going back again to our definition of cube root, if I know the volume of a cube is 8 and I want to find the side length, I just need to cube root. So that would be the cube root of 8 times the cube root of 8 times the cube root of 8. So similar to our example above, we can use logic to determine that 8 to the 1/3 is the exact same as the cube root of 8. So they are just written in different forms. 8 to the 1/3 is our exponential form, and the cube root of 8 is our radical form because it's using a radical sign. So what you'll notice is that the base of our exponent becomes the radicand in our radical expression. We're looking at the exponential piece. The denominator becomes our index. The numerator stays home with our radicand. Or again, it could also be written this way, the cube root of 8, and then the 1 is outside the brackets. So example 3 and 4 are asking us to convert from radical to exponential form and vice versa. With example number 3, we're converting from a radical to a power. And so I have root 25. Remember that my index is 2. The radicand becomes my base, so my base is 25. And the numerator would be the exponent that's with the 25, so that's a 1. And the denominator is 2. So I think about that as this guy's living outside and he wants to come home. So we say, sure, you can come on home, but you got to live in the basement. So the one that's kicked out the door comes home, but he lives in the basement. If I want to convert from a power to a radical, I have 18 to the 1/4. 18 is my base, so that becomes my radicand. So I can write 18, draw my radical sign. Now this guy here is living in the basement. That's my denominator. My denominator becomes my index. So this guy's living down in the basement and parents say, time to get out, kick you out the door. He's going to stay outside. And then the 1 stays home. Again, you can write that as the 4th root of 18, brackets, and then the 1. So I want you to pause the video, try the remaining examples, and then come back and check your work. So let's take a look at your answers. The cube root of 64 can be written as 64 to the exponent 1/3. It's important to know that all of these can be checked with your calculator. If I took the square root of 25 and I also calculated 25 to the exponent 1/2, I should get the same answer. Now, if you're working with a TA83 plus, those brackets are going to be very important. TA84 plus, you'll notice that your calculator automatically puts the exponent in exponent land. If I wanted to check another one here, the cube root of 29, so the 4, so math 429, close your brackets to the exponent 5, or we could also use the brackets, bracket math 429, close your brackets, and then put it to the exponent of 5. You'll see that they're the same answer. If I wanted to calculate the exponential form, 29 to the exponent 5/3. Again, those brackets are important with that TA83 plus. We're going to have 273.7. So we can always use our calculator to verify our answers. For example 4, 512 to the exponent of 2/3 can be written as the cube root of 512 squared, or the cube root of 512 in brackets and then squared. And our last example, 12 to the 1/2, is root 12. And again, remember that if you wanted to, you could absolutely put that 2 in as your index. Whether you put it there and don't doesn't matter. What does matter is if your index is anything other than 2. If something is a cube root and you don't put the index, the answer is actually incorrect. Now, before we move on to the second part of our lesson, I want to talk very briefly about exact versus approximate. As you move further into your high school courses, especially in the Dash 1 stream, you're going to find that more and more your answers need to be left exact. So what does that mean? If I were to evaluate root 9, I would get 3. If I were to evaluate the cube root of 8, that would give me 2. And if I were to evaluate the root of 7, that would give me 2.64575, and on and on. Root 7 is an irrational number. It goes on forever with no repeating pattern, so a non-terminating, non-repeating decimal. And so what I'm writing is an approximation. Root 9 is 3. That's a natural number. It's not rounded. It's just a terminating decimal. This is an exact value. For 2, this is also an exact value. Now, the root 7 is exact, and this decimal value is just the approximation. So again, just be careful to check, are you being asked for something to be exact or approximated? So as we move into the next part of our lesson, we're going to be looking at how to express our radicals as exact values in simplest form. In this part of the lesson, we're going to be looking at how to convert radicals from entire form to mixed and mixed to entire. So first of all, we want to talk about what those two terms mean. If something is an entire radical, that means the value of the radical is entirely under the radical sign and it has a coefficient of 1. So that means there's nothing standing outside of the radical sign. Some examples: root 10, root 253, the cube root of 94, and the fifth root of 32. Once again, our x would be our radicand. We've got the root sign, and the n would be our index. So if something is an entire radical, everything is entirely under the radical sign. So we just have our root with our index and our radicand. If something is a mixed radical, that means the radical has a coefficient other than 1. So there's something outside of that radical sign. Some examples would be 3 root 5, 4 root 7, negative 5 times the cube root of 17, and 4 root 18. Now, as we start looking at simplifying radicals, going from entire to mixed, it's going to be really important that you remember those perfect squares. So I have the numbers listed here, but when you're working on your daily practice or an assignment or a test or quiz, it's going to be really helpful for you to write that list out for yourself. So just getting in the habit of having those numbers listed down, seeing them visually can often help sort of speed up the process when you're breaking down your radicals. The process of converting an entire radical to a mixed radical in simplest form is an essential outcome. You are going to see this throughout high school, especially in the Dash 1 stream, but you'll also see it in 20-2. If this is a concept that you're struggling with in any way, shape, or form, make sure to do some extra practice, reach out to your teacher, ask for help as you need. It's really important that you master this skill, as it's one that you're going to see quite frequently. All right, so we're asked to write each of the following as mixed radicals in simplest form. So there are a number of different ways that you can write out your work, and I'll show you those as we're working through. Essentially, what we're doing is trying to find the biggest perfect square that we can pull out of our radicand so that we can simplify that entire radical. So there are a number of different ways that you can write out your work, and I'll show you those as we're working through. Essentially, what we're doing is trying to find the biggest perfect square that we can pull out of our radicand so that we can simplify that entire radical. So here I have the square root of 8. If I want to simplify root 8, I first want to think about my factors of 8. So that's 1 and 8 and 2 and 4. And if I look at that list of factor pairs, the only perfect square that I have is 4. This can then be written as the square root of 4 times 2, which can also be written as root 4 times root 2. Now the square root of 4 is 2, so that can be simplified, and root 2 cannot be broken down any further. So the square root of 8 in simplest form as a mixed radical is 2 root 2. Now it's very easy to check my work with my calculator. I can type in the square root of 8 and 2 root 2, and I should get the same decimal, which tells me I've done this correctly. So if root 2 can't be broken down any further and root 8 is equivalent to 2 root 2, I know that my answer is correct, so I can box and move on. So for root 12, again, I think about my factors. I've got 1 and 12, 2 and 6, 3 and 4. Once again, I only have one perfect square there, and that's root 4. Another way that I could think about this is to look at my perfect squares. So my perfect squares are 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. Well, 16 is bigger than 12, so I don't have to go any further. So I start looking back at my list, and the only perfect square that goes into 12 is 4. So whether you do it by listing your factor pairs or looking at your list of perfect squares, you can still identify the biggest perfect square that we can pull out. Another way that you can write this is as a factor tree. So if I have root 12, that can be root 3 times root 4. Root 3 can't be broken down any further. Root 4 is 2. So I will typically write my coefficient first. So that's 2 square root 3. So let's take a look at root 32. I'm going to write out my perfect squares. So I've got 1 squared, 2 squared, 3 squared, and so on. And once I get to 36, that's bigger than 32, so I don't have to go any further. When I look back through this list, 16 goes into 32 and so does 4. But once again, I want to pull out the biggest perfect square, so I'm going to work with 16. Now for myself, I find that I can mix up my numbers quite a bit. So a strategy that I've used for myself is to always write my perfect square first. So root 16. Now 16 times 2 is 32, so this is going to be root 16 times root 2. The square root of 16 is 4, so that's going to give me 4 root 2. And if I wanted to make sure that I was correct, I would double check on my calculator. The square root of 32 gives me that decimal, and 4 root 2 gives me the same decimal, so I know I'm correct and I can move on. Here we have a mixed radical. It's 3 root 500, but it's not in simplest form because the root 500 can be broken down. Sometimes it helps to make your list. Other times, if you know your factors really well, you might already have an idea what that perfect square is. I know that 5 times 100 is 500. I know that 100 is a perfect square, and I know that root 5 can't be broken down. So without making my list, I know that this is going to be root 100 times 5. So I'm going to write this as a radical. Again, just showing you that there's different ways to write it. And using my strategy, I'm going to put my perfect square first, just so that I know that's the one that's coming out. I've got 3, and then I'm going to put a bracket because this is going to be simplified. The square root of 100 is 10, so that comes out. And the 5 stays underneath as a radicand. Now, when I've pulled that 10 out, I can now multiply the 3 times the 10. So this is going to give me 30 root 5. And again, that can be verified with my calculator. Okay, so I'm going to actually skip E and go straight to F. Here we're looking at breaking down the cube root of 40. So this time we're looking at our perfect cubes. So I can list my factors of 40. So 1 and 40, 2 and 20, 4 and 10, 5 and 8, and that's all of them. This time I want my perfect cube. So if I go through my list of perfect cubes, the only one that I have is 8. So that's the one that I'm going to work with. So I can write that as the cube root of 8 times 5. Again, using my strategy. The cube root of 8 will come out. That's going to be a 2. And then I'm left with the cube root of 5. If you wanted to write that as a factor tree, I'd have the cube root of 40 is the cube root of 8 times the cube root of 5. The cube root of 8 can be simplified further. Still going to leave me with 2 times the cube root of 5. And we can verify with our calculator the cube root of 40, and then 2 times the cube root of 5 should give me the same answer. We left our final answer as root 18, but now we know that can be simplified further. So we start off by listing our perfect squares. We've got 1, 4, 9, 16, 25. Well, we know that it's not going to be anything bigger than 16, so it has to be one of these. Well, if I look at those numbers, the only one that goes into 18 and is a perfect square is 9. So we can write that as root 9 times root 2, and root 9 breaks down to 3. Or we can write this as root 9 times 2, the square root of 9 is 3, that comes out, and we're left with 3 root 2. So root 18 is the same as 3 root 2. So this would be our answer written in simplest form. All right, so I'd like you to pause the video, try the remaining 3 examples, and then come back and check your work. So let's take a look at your answers. Here we have root 108. When I made my list, I had quite a few numbers in there that were perfect squares that went into 108, but when I'm working backwards, the biggest one is 36. So the square root of 108 can be broken down to the square root of 36 times the square root of 3. Square root of 36 is 6, and then root 3 can't be broken down, so I'm left with 6 root 3. Looking at G, the cube root of 54, when I make my perfect cubes list there, you'll notice that the only perfect cube that goes into 54 is 27. The better you know your factors, the quicker you're going to start to recognize which numbers or which perfect squares or perfect cubes you can pull out of that radicand. So here I have cube root of 27 times the cube root of 2. Cube root 27 can break down to 3. I'm left with 3 times the cube root of 2. Again, it's very easy to mix up your numbers. You'll find yourself writing 2 times the cube root of 3. So that's why it's really important to always double check on your calculator. So just being diligent to check for those silly writing errors or silly calculator errors and use your calculator to check your work. Here we have 2 times the cube root of 128. So when I look at my perfect cubes, I've got 8 and 64 that both go into 128, but the biggest one is 64, so that's what I'm going to work with. So I'm going to have 2 times the cube root of 64 times 2. The cube root of 64 can be broken down and gives me 4. 2 times 4 is 8, so I'm left with 8 times the cube root of 2. Now, if this method isn't working for you and you need another way to break down those radicals, there is another way to break down or simplify radicals using upside down birthday cake. However, I'm going to wait until the end of the video to show you that. So we're going to move on to converting from mixed to entire radicals. Now, when we're converting from mixed to entire radicals, essentially we're just reversing the process. So when we were simplifying the entire radicals, we were taking the biggest perfect square, biggest perfect cube that was in our radicand, we were rooting it or cube rooting it, whatever the index was, and that became our coefficient. So if I want to have 4 root 3 and convert it back to an entire radical, that 4 has to go back under the radical sign. And we have to do that by raising it to the exponent of the index. So in this case, my index is 2. So in order to put that 4 back underneath the radical sign, I need to raise it to the exponent 2. So it would look like this. 4 to the exponent of 2 times 3. Now 4 squared is 16, so 16 times 3, which is 48. And once again, I can check that on my calculator. 4 root 3 should give me the same decimal as the square root of 48, and it does. If I wanted to work with an index of 3, this would be 5 to the exponent 3 times 2, all underneath the cube root. 5 cubed is 125, and 125 is 2. So 5 cubed is 125, and 125 times 2 is 250. So 5 times the cube root of 2 is the same as the cube root of 250. So this method works for all indexes. If I had 3 times the 4th root of 2, that's just going to become 3 to the 4th times 2, which becomes the 4th root of 162. Now, working with those higher indexes can be a little bit tricky when we're putting them into our calculator. So we're going to go through one example here. If I want to do 3 times the 4th root of 2, I'm going to type 3, open my bracket, type my index, math, choose 5, and then type in my radicand and close my bracket. If I want to do the 4th root of 162, type your index, math, 5, 162, and once again, they have the same decimal, so I know I'm correct. Okay, so that gives you some examples. What I'd like you to do is pause the video, try the remaining questions on your own, and then come back and check your work. Okay, so let's check your answers. 5 root 2 should give you root 50. So 5 squared times 2. 3 root 7 would be root 3 squared times 7, which is root 63. 4 times the cube root of 5 would be the cube root of 320. 2 times the cube root of 9 would be the cube root of 72. And lastly, 3 times the 5th root of 12 would be the 5th root of 2916. Now, if you were having trouble putting any of that in your calculator, 3 to the 5th would be 3 exponent 5, and then we could multiply by 12. So example 7, I'd like you to try on your own. You're asked to order the following by first writing as entire radicals. Now it doesn't actually tell you how to order, so let's go with ascending order, which would be ordering from least to greatest. So what you're going to do is take each of those mixed radicals, convert them to entire radicals, and then order them from least to greatest. So let's take a look at your work. As it turns out, in this particular example, the expressions were already ordered from least to greatest, but when you were converting, you should have had 2 root 5 giving you root 20, 3 root 6 giving you root 54, 4 root 12 giving you root 192, and 9 root 3 giving you 243. So when you have radicals that all have the same index and you're being asked to order them, you can convert everything to an entire radical, and then it's really easy to see which is your lowest and which is your highest. So earlier I mentioned an alternative method to converting from entire to mixed radicals in simplest form. And I'm going to show you that here using birthday cake. Now before that, what I want to do is just a quick refresher. If I have root 12, what I've been showing you to do is look for the biggest perfect square that goes into 12. That's going to be 4. 4 times 3. Well, the square root of 4 is 2, and then my leftovers are 3. So root 12 and 2 root 3 are equivalent. If I want to use birthday cake, the first thing I have to do is get my prime factors. So I'm going to have 12. 12 divided by 2 is 6. 6 divided by 2 is 3. And 3 divided by 3 is 1. So 12 is 2 times 2 times 3. Because I'm square rooting, I'm looking for a perfect square, so I'm looking for pairs. So I have a pair of 2's here, and for each pair I pull out the number once, so that's going to leave me with 2 root 3. So let's look at 3 root 500. First of all, I'm going to break down 500 into its prime factors. So 500 divided by 5 is 100. 100 divided by 2 is 50. 50 divided by 5 is 10. 10 divided by 2 is 5. 5 and 1. So this time again, I'm looking for an index of 2. I'm square rooting, so I have to look for pairs. So I have a pair of 5's here, and I have a pair of 2's here. So 5 and 2, so 5 times 2 is 10. And notice I have a leftover of 5. Now remember, I still have that 3, so that has to come out. 3 times 10 is 30, and I'm left with 30 root 5. Now the process is exactly the same when I'm looking for cube roots, except instead of looking for pairs, I'm going to be looking for triples. So again, I'll start by breaking down 40 into its prime factors. 40 divided by 2 is 20. 20 divided by 2 is 10. 10 divided by 2 is 5. 5 and 1. So 5 times 2 times 2 times 2 is 40. Again, I'm looking for triples. So there's a group of 3's. So I'm going to pull out a 2, and the rest stays underneath. Don't forget to use your index. 2 times the cube root of 5. So again, this is just an alternative method. I don't necessarily think this is the most efficient method, but if you are struggling to break down your entire radicals using the method I showed you in the beginning, this could be an alternative option for you. That's everything I have for you guys today. This is, again, a very important concept. It's one that you're going to see a lot, so make sure you do practice, ask questions as you need. Have a good day, and we'll see you next time.